Great. Thanks so much. Good afternoon, everyone. My name is Rally Chakarova, and I'm the Executive Director of the Toronto and Area Road Builders Association, or TARBA. Our members perform a majority of new transportation construction and maintenance for municipalities, Ontario's Ministry of Transportation, Metrolinx, and other provincial agencies, as well as residential and industrial project owners. One of our biggest efforts is promoting the increased use of recycled crushed aggregates in the construction of linear infrastructure in our region and beyond, and I'm thrilled to be here today to present on its use and answer any questions. I want to start off by playing a quick video that outlines the opportunity.
Today's roads define tomorrow. For our communities to thrive, we need to build the infrastructure to support them. But as our cities grow, so does our impact on the environment. Every day brings us closer to exhausting our aggregate supply, the essential construction materials for the housing, transit, schools, and hospitals we rely on. The further we need to travel for or ship these materials, the more expensive it is to build, and the greater the environmental impact. But there is an alternative, a cost-effective, sustainable way. As we replace old roads and sidewalks, we can take the rubble to local recycling plants, where it is crushed, cleaned, and sorted to a standard provincial requirement, and repurposed to build new roads, subdivisions, highways, bridges, and tunnels. The same safe, engineered roads for our families to travel on, built sustainably with our children's future in mind. Every kilometer that uses recycled aggregates reduces the need to mine new resources, keeps valuable construction materials out of landfills, reduces carbon emissions and pollution, limits traffic congestion, and reduces the financial strain on municipal budgets. Countries around the globe, Toronto Pearson Airport, and our 400 series highways here at home have all used recycled aggregates in their expansion and new construction, demonstrating the durability, safety, and high performance of recycled crushed aggregates. And now, we're urging Ontario municipalities to adopt sustainable building practices and prioritize the use of recycled materials. With a recycling rate of just 20%, municipalities can make a positive change. This is clean air, less waste, and a future where growth doesn't come at the cost of our planet. The roads we take define us. Let's build a greener future we can all be proud of.
So with that, I'm going to dive a little bit more into the context here. Oops. Thought that would happen. Perfect. So I think many of you might be aware that we are looking at continued population growth in Ontario and a growing state of good repair backlog, both of which require us to build more and maintain our existing transportation and housing infrastructure. We've also seen construction costs rise, especially during and after the pandemic, and as we deplete close to market sources of aggregates, those costs will only rise. And as roads are repaired, sorry about that. And as roads are repaired, bridges are maintained, and other critical infrastructure is replaced or expanded, tens of millions of tons of asphalt and concrete are removed from construction sites across Ontario. And if they're not recycled and reused, these valuable materials will end up in landfills, further exacerbating our landfill capacity. So to start off with some definitions, and to dive into our discussion today, as you saw from the video, and as many of you probably know, asphalt and concrete are 100% recyclable and can be reused as valuable construction materials. So I do want to clarify, because we get this question a lot, as to what we mean by recycled crushed aggregates. So we have RAP, which is a reclaimed asphalt pavement. We have RCM, which is the reclaimed concrete material. And the main topic of today, recycled crushed aggregates, is reclaimed asphalt pavement and or concrete. And in our view, RCA is a sustainable product that offers some of the greatest environmental benefits at a low cost. These materials have already met performance specifications when they were originally used, and when reclaimed, they undergo an additional rigorous process of crushing, screening, testing, and quality control to be repurposed for their intended application as construction material in new projects. Extensive testing in Ontario and internationally has shown that RCA is a high-performance material for an increasing number of applications, with numerous studies concluding that its geotechnical properties are equal and sometimes superior to primary aggregates. And I look forward to Salman walking us through some of those results later today. In fact, when RCA conforms to Ontario specifications, or OPSS 1010, project owners can be confident that these materials will meet all performance requirements and quality expectations. As most of you know, the OPSS 1010 is administered jointly by the Ontario Ministry of Transportation and the Municipal Engineering Association, and also includes representatives from the construction industry. So the spec as it is right now allows aggregate use in road bases, shoulders, and backfill to be composed of up to 100% recycled concrete and up to 30% recycled asphalt. And hot mix asphalt can also contain up to 30% RAP. However, despite this provincial standard, municipalities have discretion in their implementation and they can set their own standards. As a result, practices can vary widely by municipality, even in an economically significant region like the Greater Toronto Area, which is made up of 25 urban, suburban, and rural municipalities. For example, municipalities have specifications requiring primary aggregate only as part of their local specs or tenders, and through that, they're missing out on the benefits RCA use offers to both municipal capital budgets and their net zero targets. As you'll see from the logos here and the video, RCA has broad-based industry support, and these 9 organizations, including Good Roads, the OSSGA, and the Ontario Society of Professional Engineers, our hosts today, are strong advocates for increased RCA use. So here's a good cheat sheet or an overview of the important direct and indirect economic and environmental benefits of using RCA. It significantly lowers carbon emissions, pollution, and project costs associated with long-haul trucking of the material while performing equally or better than primary aggregates. The shorter distance traveled also means less traffic congestion and wear and tear on roads, and RCA also preserves non-renewable resources and extends the life of existing pits and quarries. And how does it do all of that? So looking to the next slide, transportation makes up to 60% of the cost of aggregates. So that means that every extra kilometer that aggregate has to be trucked to a job site, it increases the overall building costs and carbon emissions. And RCA is available at a fraction of the distance to the new construction sites. The chart to the left, provided from research from EXP, estimates the fuel consumption and associated greenhouse gas emissions for the 25 million tons of aggregate produced in the GTA. As expected, longer distances traveled require more fuel and emit significantly more GHG emissions. Now, as part of that research, 4 projects were examined, from a parking lot to a big box store distribution center in the Greater Toronto Area. The research found that the higher amount of RCA used on a project, the bigger the cost savings and carbon reductions. On average, across the 4 projects, the savings were about $8 per ton, and the carbon emission reductions between the primary and recycled aggregates were predominantly derived from the shorter distance traveled. So you'll see here on the chart, we have 18 kilometers versus 80, 66 versus 115, 10 versus 52, and 14 versus 70. And you'll see that the more aggregate that is used on a project, the higher the savings. So for 11,000, you have 77,000 in savings versus 100,000 tons, which is 900, almost $1 million in cost savings. Next, I want to share with you 4 examples of RCA use in Ontario. The first is the Ontario Ministry of Transportation, who has used RCA in the expansion and maintenance of its extensive 400 series highway network dating back to the 1970s. On this particular expansion of a 9-kilometer highway stretch, MTO used 300,000 tons of RCA, generating $1.2 million in cost savings for taxpayers. The RCA source was less than 10 kilometers to the project, generating significant carbon reduction emissions. Second to that, and on our topic of performance, back in 2006, Toronto Pearson Airport set the example for material reuse, recycling, and remediation with the demolition of Old Terminal 1, which at that time was Canada's largest demolition contract. 250,000 tons of rubble was crushed, screened, and recycled on site to be used as the apron subbase holding up the final apron structure. Since the process took place on site, it significantly reduced carbon emissions from long-haul trucking. In 2022, Pearson reused another 25,000 tons for the rehabilitation of its second busiest runway, once again showing no structural failures or additional maintenance requirements. My most recent favorite project is the Viva Next massive transit expansion in York Region, located just north of Toronto, which used more than 250,000 tons of RCA just in its Yonge Street expansion alone. And that's the blue line that you see on the map there. Also on the map to the right, the red line is the RCA source, which was just 19 kilometers away from the project, compared to the 64 kilometers to the Deference Pit in Milton, which is in the bottom left corner. So more than 5,500 truckloads of demolition rubble were taken to the recycling plant to be reused back in the construction of the rapid bus route. So an additional benefit I'd like to highlight here is that after the rubble was dumped, the vehicle would backhaul material back to the project, minimizing empty loads as part of the project operations. We have 6 years later and many good Canadian winters. York Region is very happy with the performance, reporting no structural issues or additional maintenance required. And you can watch that full webinar on our YouTube at Road Builders. And the last project I want to share is one from East Gwillimbury, again, north of Toronto, that has a population of just over 35,000 people. And through its Thinking Green standard, it requires 30% of recycled materials to be used. In 2021, however, their Queensville subdivision used approximately 88% of recycled material, generating $152,000 in savings for the project. And I've included this example because it's a small municipality and it shows that those still can tap into the benefits through thoughtful policy direction and by using the OPSS guidelines. And you saw that the video largely focuses on municipalities. So why municipalities? And the short answer to that is because that's where the biggest impact for RCA's economic and environmental savings can be seen. In Ontario, just over 50% of all aggregates are used in the construction of roadways, bridges, and tunnel infrastructure, and all of those can be built with RCA. As you probably know, municipalities own and manage more roads than the provincial and federal governments combined, and they are the largest consumer of aggregates, using 60 to 70% tons per year, and 50% of their budgets are allocated to construction and infrastructure. All of that in the context that more than 500 municipalities in Canada have declared a climate emergency, and even more have net zero targets that they're hoping to accomplish. And from a municipal and provincial perspective, RCA is also the solution to two big land use issues that take place at the local level. And that's reducing construction waste in our landfills and extending the life of existing pits and quarries. I'm sure if you live in a municipality that's close to one of those, or you work as part of policy development, you've seen that it generates a lot of resistance, and it's quite a contentious issue for those local communities. Ontario has less than 10 years until all landfills in the province are full, and that's according to a live countdown run by Waste to Resource Ontario. At the same time that aggregates are the foundational material for the critical infrastructure our growing communities need. And even in a resource-rich area like the Greater Toronto Area, we already have an aggregate deficit here. The region produces 25 million tons, but it consumes 73 million tons, and that is projected to rise to 1.5 billion by 2041, all while exhausting close-to-market sources. And as I mentioned already, the further we need to travel for our aggregates, the higher the cost of construction and our impact on the environment. And just sharing the top line of the stats here that you quickly saw in the video, if municipalities across Ontario adopted a recycling rate of just 20%, it would avoid extracting up to 33 million tons of new aggregate per year across the province. This would result in annual savings of 264 million and greenhouse gas emissions equivalent to taking 15 million gas cars off the road for an entire year. And just in case you're wondering, that's a lot more than all the cars that we have here in Ontario. 20% was selected as an achievable target, demonstrated for decades by the Ontario Ministry of Transportation, proving the cost and sustainability benefits while maintaining that performance. And as you'll see throughout the remainder of this presentation, the key aspect in using RCA successfully is quality control, as is with any other material use. So as mentioned at the beginning, research has shown that when RCA conforms to OPSS 1010, project owners and contractors can be confident that these materials will meet all performance requirements and quality expectations. This is why we very strongly encourage that all efforts should be directed to enforcing quality rather than restricting the use of the material. On the website rcaontario.ca, you'll find the TARBA quality control plan that provides a technically sound manual for the production, utilization, and ensuring the quality of recycled crushed aggregates. And that can be used as a great resource for both producers, contractors, and project owners. The last slide I'll leave you with before I hand it over to Salman is that, in our view, both public and private project owners can unlock the benefits of RCA by prioritizing sustainability as part of the initial project design. So more specifically and tangibly as action items, the first and foremost would be including RCA use as part of the tenders. In some cases, we've seen that even if a municipality has specifications that allows the use of RCA, once tenders come out, they still specify primary aggregates only. So it's really important to include RCA use as part of the tenders in order to be able to tap into those project cost savings as part of the initial bids. Align municipal standards with the OPSS 1010, having a smorgasbord of different standards, municipality to municipality, actually erodes the consistency and performance. It increases administrative burden, and it really actually discourages wider adoption. So aligning those municipal standards and capitalizing on economies of scale as part of the production of the material will only benefit project owners, contractors, and suppliers. And lastly, collaborate with industry. The projects that I've shared have been great public-private partnerships with the builders, and that's really to tap into the internal capacity and confidence of quality control measures and ensure that the applications are appropriate and the material is used to its greatest abilities. On the same website that I mentioned already, rcaontario.ca, you'll find additional resources, including the EXP research, the research by Engtec that Salman is going to talk to shortly, as well as the Viva Next case study and other webinar presentations on the topic. So with that, thank you again for your time. And now I'll pass it on to Salman to provide an overview of the research and answer the technical questions. Thank you.
I'm going to share my screen now, and assuming everything is clear over here. Thank you very much, Riley and Victoria. Good afternoon, everyone. My name is Salman Bhutta. I'm the principal at Engtec Consulting, Inc. Engtec Consulting, Inc. is a civil engineering consulting firm based out of Toronto. We also have an office in London. And so giving us coverage Toronto as well as Southwestern Ontario. We have a fairly large footprint in engineering and materials testing, including complex material testing, which is not run-of-the-mill stuff. So as part of that work, this discussion came up with TARBA, and the main item over here was, can we evaluate crusher on limestone, crushed concretes, granular base equivalency, and structural number, and see what are the real-time differences in between these materials. So that's the topic of today's discussion. This is a bit of a technical background to it. I'm going to talk about some numbers, but in the end, it is all going to gel up into a one formal conclusion, which is going to give these answers to these questions that we have in our mind. Is crushed concrete good or is crushed concrete bad? Is it structurally sound or is it structurally not sound? So with that in mind, I took the liberty of setting up a setup of this presentation where I'm going to talk about a background as to why we are doing this. We're going to talk about assessing the granular base equivalency and structural number of crushed concrete. How did we assess it? How did we test it? We're going to compare it with materials which we deal with as a standard in the industry, which is virgin granular A's and granular B type 1s, type 2s, and crusher and limestone type material, which we are very familiar with. And then I'm going to try to wrap it up with a conclusion and recommendations as to what we found out of this study and how can we utilize it in pavement designs and replacement of one material with the other. So just to go through a background over here, the use of recycled materials, namely crushed concrete, it's gaining quite a bit of momentum in the industry. About 20 years ago, it was a question mark element, but about 20 to 25 years ago, early 2000s. But now it is widely used in municipal, private, and provincial projects all the time. Recycled materials reduce the demand for virgin aggregates, minimize waste, and contribute to a sustainable construction practices. However, a critical aspect of this adoption is the need to ensure that the structural integrity and the performance of the materials, namely crushed concrete, is comparable to traditional materials like virgin granular materials or crushed and limestones for that matter, or sand and gravel materials for that matter, which we have been using forever in the industry and have a long history. Keep in mind, crushed concrete has over 25 years of history also at this point in time from a technical perspective. Despite these benefits, acceptance of crushed concrete by project owners still remains inconsistent. And that you see a lot of times when in projects you are allowed to use it, but then when it comes down to proposals to implementing it, here is the product, it is refused. And I've been involved with projects where it is refused. And there are certain uncertainties around its performance. Some of them are true, some of them are not true. Some of them are based upon earlier crushed concretes from early 2000, which had bits of issues here and there. But things have improved significantly since then. And so this study offers a thorough evaluation of structural numbers. And those of us who design pavements, we are aware of structural numbers and how do we calculate them. And granular base equivalency, this is a concept from 1990s and earlier of crushed concrete, comparing it to performance and comparing its performance to standard materials, which is virgin materials for that matter. What Tarba has noted is inconsistencies in how the structural strength of crushed concrete has been assessed over the past 2 decades. In some regions, crushed concrete layer thicknesses, they are arbitrarily increased 10 to 15% thicker. Say if you're going to put 150 millimeters of A or for that granular A virgin, if you want to use crushed concrete, we need 15% or 20% more, whatever criteria. So it's very randomized selection of acceptance of this material, as opposed to crusher and limestones or 50 millimeter crusher and limestones for that matter. So this additional thickness requirement stems from a perception that the crushed concrete is an inferior product, and consequently, it is not comparable to virgin materials. So hence this study to try to figure out, is it structurally inferior or not? So this study seeks to challenge that perception and provide some data that supports the equivalency of these materials. The tests are intended to demonstrate that crushed concrete can perform as well as traditional materials without the need of any increased thicknesses and we will discuss some testing over here also. How to go about getting them approved. Furthermore, this is recognized by Ministry of Transportation Ontario because in most of their projects they consider it as an equivalent, although Ministry of Transportation Ontario has a granular B type 1 equivalency. They do not allow it to be used in granular 2 as a granular B type 2 material, and that's kind of, we will discuss it toward the end, is mostly based upon early 2000 assessments that were done, and the materials in those days were a little bit different in terms of quality also. So by establishing the equivalency of these materials, this study aims to promote a wider acceptance and use of crushed concrete in the construction projects. And the main objective is to ensure that sustainable materials are incorporated, as Raleigh indicated, without compromising structural performance of pavements and in linear infrastructure. So now I'm going to jump into that study. So last year we were in conversation with Tarba, and they require some complex testing to prove this stuff. So essentially, we are talking resilient modulus type tests, which are not very common, and they're mostly university type entities that do those tests. We are lucky at Engtec that we have the infrastructure and the equipment and the expertise to do those tests. So we set up a program for them whereby we picked up 3 different types of crushed concrete supplier samples. We picked up 19 millimeter crushed limestone, crushed concrete, 50 millimeter crushed concrete. There are suppliers, but I just call them A, B, and C to keep that confidential. Their materials are different in look, in terms of some physical properties also, which I would detail in the upcoming slides, but there were 3 different suppliers that were tested. Can we test 10 different suppliers? Yes, we can, but right now we tested 3 different suppliers over here, and they are major suppliers in the GTA area. Then we tested crushed limestone. This is a fairly standard, comes out of the Milton quarry or Lafarge Dundas, and it is a fairly high-end product with a very high cost, by the way, 19 millimeter and 50 millimeter products in that case. This is essentially 50 millimeter crushed limestone is like a granular B type 2 material. And then we went to a sand and gravel source. So we went to like a virgin granular A, 60% crushed, virgin granular B type 1. It says type 1. It says type 2 over here, but that essentially it kind of falls in the type 2 category, although because of its crush count. But it is from a Lafarge Caledon sand and gravel quarry spit. So something about testing standards. We tested everything in this material matrix for OPSS 1010, physicals, gradations, everything under the sun. We had tested it completely. And then we went in and did, as per AASHTO T307, something called resilient modulus testing. The resilient modulus testing, this is for granular and soil materials. I'll show some pictures over here for this particular test also as we move along, and I'll give you the background for that test also. It's like under dynamic loading, so it's looking at how these recoverable strains and applied loads are managed by the materials in question. So it gives you a strength indicator. That's the item that kind of plugs into structural numbers and granular base equivalencies for that matter. So testing methodology and engineering analysis perspective, we determined the resilient modulus of each material. We evaluated the granular base equivalency of each material, because some of us, we still go back to granular base equivalencies for municipal jobs and private entities for that matter, and we still do granular base equivalency because it's a concept that's been there for 40 to 50 years. And then we went ahead and did the structural number assessment. based upon resilient modulus analysis. So the equipment we used for this is called a UTM-30 machine. It's manufactured by Controls out of Italy. It's a dynamic loading frame, and we need a triaxial cell setup. For those of us who are a little bit aware of material testing, it's like a pressurized chamber that you can create all sorts of confining pressures in. Some references: adaptation of AASHTO pavement design guide for Ontario conditions, MI 183. It provides some guidelines as to what values should be used for design purposes or structural design purposes. Pavement designer rehabilitation manual STO 90. This primarily deals with granular-based equivalencies related elements. And the second edition deals with structure number, which is 2013 of the edition deals with that. And then standard, this AASHTO T 307 standard, which is the standard method for test for determining resilient modulus of soils and aggregate materials. So little graph, not to confuse anybody, but for us engineers, we can understand what is going on over here. Every material in the world has a viscoelastic, other than rubber, has a viscoelastic behavior. It's an elastoplastic material. You apply a load and you will have some level of strain, some level of deformation or strain that never comes back. And there is some which is recoverable, some level of load application. As you apply a sinusoidal load on it, it has a recoverable strain and it has a non-recoverable strain. This is permanent deformation, relates to permanent deformation. And this is deformation that is more falling in an elastic manner, and it is recovered after every time the loads are applied. So this is the concept that relates directly into how resilient moduluses are assessed, because it's a dynamic load. So in a triaxial cell, if you can imagine a piece of gravel somewhere in a cubic centimeter of gravel, somewhere in the middle of gravel, it has a confining pressure around it. And it has, and every time a vehicle goes by, a load gets applied to it. And that's exactly what is being simulated in this type of a mathematical analogy. So this is the applied load, this is the confining pressure, and then you can calculate the resilient modulus if you can determine the recoverable strain, and you know these applied values, which the equipments nowadays can easily measure. You can assess the resilient modulus of the material. And you can determine with quite a bit of accuracy what this material is from a strength perspective. This is the equipment that is used for these purposes. This is a UTM-30 machine. It's a loading frame. This is the dynamic loading frame on the top. It has the capability to apply about 30 kilonewtons of load. There is a much bigger version of this machine available also. It can apply up to 130 kilonewtons of load, but your resolution starts to reduce as you go to higher load levels. So for our practical testing in this setup, a 30 kilonewton load cell is what is more acceptable, because it has fairly high precision at that point in time. I'm going to try to zoom in over here. This is a setup of the resilient modulus testing. You'll see what it has is that there's a triaxial cell. This is linked to a pressure, so it generates a confining pressure. And then you have this load cell come down and apply dynamic load on it. This is the sample. We need to always put this sample in a form, because you cannot really form a gravel or a soil sample like a strong, long tube. So you typically have to put it in something like this. It's like a latex membrane. And it doesn't generate any, all it does is to hold the sample in one form. It's a pretty standard way of doing things in testing in the dynamic mode of using the loading frame for soils and granulars. So this is the setup that is used in order to do the testing as per AASHTO 307. We are measuring recoverable strains, and we are also measuring the stresses and strains. So all these things are logged into a data acquisition, and then we go about and do a calculation to figure out what these values are. Big question over here is what kind of confining pressure should you be using? Now, we can't just randomly pick numbers out as to what we should be doing, but just to give you a good idea, you have to do some mathematical background and some calculations into figuring out what kind of confining pressures you have to use. So you really need to set up this model over here, as you see in this area. And you have to, and this is a typical 100 millimeters over 150 of A over 300 of B, a typical pavement, and trying to figure out what is the stress, confining stress over here, and what's the confining stress over here, like in the lateral directions, due to a standard applied load. So when we evaluated that using linear elastic analysis, we figured out that at this step, the confining pressure reduces to 95 kPa. And within the granular A layer, it is about 140 kPa. So we need to pick the closest numbers for confining pressure that we can apply. So the selected values of interest for us are 103 kPa and 137 kPa, which are very close to these values. So if you want to evaluate granular B, you're somewhere in the 103 kPa, and you're lower down into the pavement structure also. And if you are at granular A level, your confining pressures are a little bit higher. It's about 137 kPa. So with that in mind, so now that we got the engineering behind these tests out of the way, now let's talk about standard OPSS testing. So all these materials were tested for physical properties before we even began to do the resilient modulus testing. So this is just a matrix showing all the results for physical properties as outlined in OPSS 1010 for crushed concrete, crusher and limestones, and virgin materials. So as you can see that they are all, even the material that is coming out of Lafarge Caledon is about 95% crushed granular A. Typical requirement is about 60. Very, very, not terribly low, but pretty decent coarse aggregate micro T-val value for coarse and fine aggregates. Now, keep in mind, if it is a weak material, this is where it will show up. And some of you might be thinking that, okay, is it a weak material? Is it comparable? That's where typically its intermaterial characteristics comes into the play, which is micro T-val. It's a fairly abusive test to aggregates. Looking at asphalt coated particles, we had approximately 17 to 18% asphalt coated particles in the materials. Some level of contamination is present. And this is like maybe wood chips, brick pieces, stuff like that. Crushed concrete has it, but it's always less than 1% in most cases. Plasticity was determined. They're all non-plastic. Sieve analysis, all of them passed the table 2 requirements. And then we did standard proctors, and this you may want to remember, I highlighted some numbers in red. Although it is A, typically we say for granular A, a proctor is 2150. Well, you'll see that the crusher and limestone is about 2260, 2150. But then crusher and limestone is around 1987, 1220, sometimes 2050. Those are the typical ranges. I highlighted these because if it is a lower proctor value, we figured out that you would have a lower resilient modulus also. So there is some relationship between proctor and resilient modulus, just from a rule of thumb perspective. Now, but is that number bad? We'll find out that it's not really that bad, but it does indicate as some lower strength. Going down to OPSS 1010 granular B materials, we tested them all. They're all above 85% crushed, and looking at it, there's still some level of contamination. There is a little bit more on the micro T-val for the coarse aggregate, but again, the materials are all pretty good. From a physical properties perspective, gradation perspective, they're non-plastic, they have a good, decent proctor number. This is typically what we have in the field when we are doing it, is between 1900 to 2000 as a proctor. but there is a material from source B, which was at 2055 for the Proctor. So these numbers do reflect. So I would expect that this particular material would have a higher resilient modulus. That's what I wanted to say. So again, based upon that, what did we do is now that we tested it with that equipment, as I explained, and we determined the resilient modulus, virgin granular is from Lafarge-Callahan, 283 MPa. For those of us who have to use a number from a design perspective or are running AASHTO MEPDG and have to enter a number, we typically say 275 MPa is the number that we typically use, between 250 to 275. 275 on the upper end. This is the resilient modulus for it. Virgin granular B type 1, I'm calling it type 1, but it is really pretty close to getting to type 2. It has about 90% crush count, but it's type 1 in essence. And you see it has quite a fairly low level of value. 220 is what we typically use for AASHTO MEPDG for the design purposes or pavement design purposes. 19 millimeter crusher on crushed concrete. Now, this is the average of the source A, B, and C. There are three sources. We have about 287. It's very comparable to the Lafarge-Callahan number. And 50 millimeter crushed concrete on an average, it's a little bit higher than the Lafarge-Callahan number. Now, when you come down to 19 millimeter crusher on limestones and 50 millimeter crusher on limestones, you would expect these numbers to be higher, and they are higher, but not terribly high. Okay, but they're within about 30 to 40 MPa higher over here. And these kind of fall in line with what we generally perceive and feel that these materials are to be present in these values in terms of strength. Going down and breaking down these numbers from a crushed concrete perspective, you remember I had pointed out some red values over here. Those are those two numbers. So you can see the one which had the higher Proctor had the higher resilient modulus also over here. This is for the granular A, or 19 millimeter crushed concrete material equivalency perspective that we are looking at. And you can see that the confining pressures are correct over here also. And so when you do this test, you will get these values at different, you run it at different confining pressures. So you have to pick the exact number. If you go and pick a higher confining pressure number, your resilient modulus will be through the roof. So it may not be representative. So you need to do some math prior to picking these numbers as to which one is really applicable to our industry. This is granular B, or 50 millimeter crushed concrete from supplier A. You see the ones which had a little bit lower value and the one which had a higher Proctor value is at around 279. So what we have to do is we can be changing these materials. So we have to kind of use an average number. So in this case, we had a sample set of 3, and therefore we are using the average value for that over here. So this kind of shows a graphical representation of what we got in the field. So if you are assuming that your granular B is about 220 MPa on an average, or 225 for virgin material, you are pretty close to this. Some are higher, some are lower. Crusher and limestone is obviously quite high. And for granular A, if you're looking at something which is around 275, all these materials are pretty good in terms of their values as assessed from lab testing. Now we move on to granular base equivalency. This is the standard method to determine granular base equivalency. So all you have to do is H1 is conventional granular A, the reference material that you're using, which is sand and gravel based granular A. And this is the resilient modulus of that material. And this is the material for which you want to determine the GBE. And this is the modulus of that GBE. All you have to do is solve this equation and you'll get your granular base equivalency. And this is what you get. You get the virgin granular A is around 1.0. 19 millimeter crushed concrete on an average is equal to 1.0. This is based upon factual data as tested and then assessed from a GBE perspective. And this is granular base equivalency. 19 millimeter crusher and limestone is also approximately in the same way, because you have to keep in mind, it's a cube root, so it kind of removes a lot of this variability in the materials when you do the mathematics to calculate that value. Virgin granular B, 0.67, and the crushed concrete 50 millimeters is 1.0 again, and crusher run limestone is about 0.9. It didn't turn out that because it reduced the variability, it cube roots out the error, so it minimizes the value. So this is what we get from a GBE perspective. Now keep in mind, this is factual test-based results. So in order to do a structure number, now you can't do the cube root analysis, so you have to almost do a rule of proportionality over here. So you want to know the structure number of an unknown material, you take the structure number of that material, reference material from 183, get the MR for the reference material from the table outlined before, and use this formula to calculate. Once you do that, this is what you get. Virgin granular A, 0.14. Virgin granular B, type 2 is 0.14, not type 1. Type 1 is 0.09. 19 millimeter crushed concrete on an average was 0.14. 50 millimeter crushed concrete on an average was 0.15. So it's a little bit better in terms of what we were expecting it to be. 19 millimeter crusher run limestone and 50 millimeter crusher run limestone, they're pretty much equivalent or better than 50 millimeter crushed concrete for that matter. So we have evaluated these numbers based upon some lab testing, which is established, as well as mathematics, which is established in this procedure. Now you do notice that I keep on saying granular B type 2, granular B type 2. Now, if you go back to the original comment in one of the slides, MTO does not allow us to use they only classify crushed concrete to be replaced as granular B type 1. And same thing exists in OPSS municipal, OPSS provincial, and we'll talk about it over here. So from a granular base equivalency perspective, crushed concrete is equivalent to virgin granular A and virgin granular B type 2 materials. Because now we are not really worried about whether it is type 1 or type 2 or what specs allow. We are looking at materials and just comparing them one by one over here. And it exhibits comparable performance in terms of load-bearing support in pavement structures. This is based upon actually factual data as presented by Raleigh earlier, and performances of this material in the field. And GBE results indicate that crushed concrete can be used in similar thicknesses to virgin granular B and granular A, virgin granular B type 2 and A. And in our assessment, there is no compromise to structural integrity of the pavement when we are using crushed concrete. From a structural numbers perspective, 19 millimeter crushed concrete is equivalent to granular A. It can be used as a direct substitute for granular A in pavement designs. It offers similar load distribution and resilience under load conditions. 50 millimeter crushed concrete performs slightly better because equivalency, it's not cube root analysis, and it performs slightly better than granular B type 2 over here. And it is determined to be equivalent or slightly superior for certain granular value layers requiring increased structural performance. So in conclusion, granular based crushed concrete is equivalent to virgin granular A and granular B type 2. And now I will explain why. So back in the late 1990s and early 2000s, there was a discussion why crushed concrete at the MTO level, why crushed concrete is not used as granular B type 2. Why cannot we use it? There were discussions based upon the quality of the material in those days, where granular B type 2 and some drainage capabilities and the load-bearing capabilities, not a significant amount of testing was done, but based upon what is said in the industry, there was a discussion and it was not allowed to be used as granular B type 2. Keep in mind, it's perfectly okay to use as granular A but how come we suddenly decided to not allow it as granular B type 2, but we are okay if we can use it as granular B type 1. But over the last 25 years, there has been a significant amount of improvement in the materials, in their quality, their QC controls, and what is in the material. Definitely what you don't want is material that has soil contamination. So that's something that falls under the contractor's purview as to how they, or the supplier's purview, how they manage it at their end. But it would become quite obvious, especially based on permeability and structural capability, if there is a contaminant in the system. And permeability included. 19 millimeter crushed concrete performs on par with A, while 50 millimeter concrete shows slightly better structural performance than granular B type 2, but for all practical purposes, it can be used as a replacement to granular B type 2. We don't need to increase any layer thicknesses or randomly increase 10-20% layer thicknesses when we are using crushed concrete pavement structures. This is more aligned with MTO protocols and specifications, although there is a question mark on the use of it as a granular B type 2. Although OPSS 1010, both muni and provincial, does not permit the use of crushed concrete as a replacement for granular B type 2, but this study demonstrates that 50 millimeter crushed concrete performs equivalently to virgin B type 2 and 50 millimeter crusher on limestone. So maybe the specifications need to be looked at again from OPSS perspective. It's a fairly cost-effective and environmentally friendly alternative to virgin aggregates. And that kind of links into what Riley was indicating earlier, and supports sustainability goals without compromising structural integrity and long-term performances. And there's significant evidence to that fact. And with that, thank you very much. And if there are any questions and all that, I think all the questions are going to be coming through OSPE at this point in time, but I'm willing to answer any questions. And I hope this brief synopsis of how we got around to figuring out these values and numbers, which we always talk about hypothetically, that, oh, it is this, oh, it is that. Now we have some data that proves that things, where they lie in the global matrix of things. Thank you very much.
Thank you so much, Salman. I haven't seen any specific questions come through, but we did answer a few of them in writing. So just to summarize, I think everyone can see the answers, but I'm happy to share the 2 PowerPoints with everyone that's attending. We'll share them with Victoria and she can pass them along. And then I've just shared the links again to where the full research is available on the website. If you go to rcaontario.ca, you'll be able to download the entire PDF document and review that on your own time or share with colleagues if you'd like. I don't see any other questions, but they're certainly welcome. I think we have a few more minutes. Oh, there's one that's come through here. Have you completed, this is someone, this is for you. Have you completed any recent reconstruction projects for municipalities where RCA was substituted for virgin aggregates in the contract?
Municipal projects? I'm sorry. Yes, every time. Region of York is full of recycled concrete now. Everywhere they are using recycled concrete. The only place where we don't ask them to use crushed concrete is under building slabs. That's not a municipal element, but if you are doing building slabs, no, because of this creep-related behavior with the asphalt coated and underneath the sewers, not above them, it's underneath, because there could be some settlement as a function of time. And so that's the only place where it is always put as a question mark, but every municipality uses them. City of Mississauga uses it, Peel uses it. You know, they just need to be made aware if they have a question, and all of them come up with questions. All of them come up with questions at their end saying, oh, is crushed concrete good? So the biggest issue and I'll just kind of delve back into it, we have had is that is Highway 427 expansion, that 1 kilometer long stretch. And then from my end, I did the pavement designs for region of York at that point in time. It had a 300 millimeters of granular acres. It was a short-term design, and it had a certain amount of asphalt. But that highway was built with crushed concrete, and that's 2005 to 2010 timeline. And forgive me if I'm wrong on that timeline, but what happened was that highway heaved significantly in winter. Up to 4 to 6 inches of heaving was noticed over there. But there was a problem with that crushed concrete. It was done, extensive testing was done over there. If you remember the company by the name Jagle, which is now Englobe, they did a lot. John Emery was involved in that. And they tested the material, and they found that there was a lot of gypsum, significant amount of gypsum. Gypsum, when water hit, it swelled up. So now what we do is every time we are looking for using crushed concrete as a submission package, we ask for something called X-ray diffraction analysis. So they just take a small pinch of this material at a lab as a QA test, and then we submit it to the lab, and they test it and figure out what are the chemical compositions. And X-ray diffraction tells you if there is gypsum present in it or not. So pretty much all the suppliers of crushed concrete do that as a regular measure at their end. So once that element is resolved, or that element is resolved in the contractor submission, it is widely used in municipal projects, widely. In fact, if you ask for a project now, pretty much everything is crushed concrete, except when it is specifically requested to be a virgin material based upon a certain specific element of the engineering issue.
Thank you. That was a great answer. And yeah, that's an important example to bring up. And it's great. And I'll give a shout out again to York Region, who have addressed this issue, as you put it, and continue to use recycled crushed aggregates in such a huge variety of their projects. And we're happy to see that. There are no other questions that I see here. So thank you everyone for your time and for your interest today. It's you can tell we're both very passionate about this topic, and please feel free to reach out to both of us if you have any further questions or you require anything else.
Thank you very much, everyone.